Okay, so we started section 2.1 last time. We're looking at reasoning and logic, and we had left off talking about compound statements. And there's three types of compound statements that we're going to work with. The one we did last time is called conjunction, okay? We're going to move on this time to something called a disjunction. And then the third type is actually called a conditional or an implication. And so let's jump back to where we were before. And I believe it looks like this. Does that look right? Okay, so a disjunction is the equivalent of an or statement. And it's true if either statement is or both statements are true. Okay, so it's true if one or the other or both are true. This is written as PVQ. The V means that it's an or statement or it's a disjunction. Okay, that's that symbol. Remember the upside down V is what we had last time, and it means and. One of the things that we see as a connection point later on is this symbol or also relates to a symbol that's U, that looks like a U that means or. We haven't done that in this class yet, have we? My other class, my contemporary math class, has done that part of it. And so that's the connection in the other order. So we'll see this symbol sort of upward facing that means or statement as well. And what we want to take a look at is we want to take a look at the truth table that results from this statement. I think it's the same slide. Yes. Okay, so we're going to create a truth table. If you remember last time, we made 3 columns. One column is the column for the statement P. One column is the statement Q column. And then the third one is P or Q. And we established last time that there's always a pattern in these truth tables. The column P goes true, true, false, false. And the column Q goes true, false, true, false. And that pattern just simply accomplishes all possibilities, right? Every possibility of trues and falses within those two statements is present in one of those rows, and nothing's duplicated, okay? And I believe that we set up a statement last time about, was it teaching math and being a mom? Yes, did I have P as my teaching math statement? Yep, okay. So I teach math, we're gonna do the same thing we did before. And Q is gonna be the statement, I'm a mom. And we're going to see if I remembered who our guests were in the hallway to bring in last time, because we're going to try and bring them in again, okay? Like in our head, not physically. Okay, so I was your first guest because I'm already in the classroom, and I come in the classroom and I use the same statements as I did before, but I'm going to put the word or in between them. So I say, I teach math or I'm a mom. And you think, why'd she use the word or? You probably would think that. That was a little bit weird to say it that way. But it's a true statement. I do teach math. I am a mom. And if I put the word or between them, it is a necessarily true statement. So 2 true statements, individually true statements, result in a true statement. It's the both part right here that it describes. If both individual statements are true, the result's true. So we call this the inclusive or. It means it includes the possibility of both. There's also something called an exclusive or statement. That's not what we're using, okay? All right, the second person I had come in, I think was Dr. Drake. Does that sound right? Dr. Drake is a male math professor. So if he comes in and he says, I teach math or I'm a mom, and knowing that I just told you he teaches math, that would be a true statement, okay? You might still also say, why did he even throw in that mom business? That was weird. But it would be a true statement. Our third guest last time, I believe, was Dr. Young. Is that true? Okay, so Dr. Young teaches over in the education department, elementary, early childhood, materials. And if she comes in and she says, I teach math or I'm a mom, she doesn't teach math, but she is the mom. And so this would be also a true statement. And then if Dr. Thomas comes in and he says, I teach math or I'm a mom, you might have to do a little quick research to know for sure that he doesn't teach math. He's actually an Old Testament professor before he was our president. But he definitely doesn't teach math, so that would be a false statement. Okay, is that all right? So looking at this one, and I'll flip back to the other one, what I want you to notice is this. When you have an or statement, the majority of your ending truth values are true, right? Lots of trues. All it takes for this to be true is one column or the other one having a T in it, right? Here, there's 2 of them that have a T. Here it has a T, here it's a T. The only way you get a false statement is if both the pieces were false. It's exactly the opposite over here for the truth tables we did last time with conjunctions. The majority of them are false, right? All it takes is one false statement to make it false. Right? It's sort of like on its head. It's the reverse of what we were just describing before. So you end up with mostly false statements when you have and statements, right? So we're going to do a truth table for an arbitrary statement that's been given to us. This statement has, I wanted it to be white, has a column for P. It'll have a column for Q. All right, this will be enough. So it will have, as mentioned, a column for P and a column for Q. We always have P's and Q's in terms of the individual columns, even if we don't have Q in the original statement. So like this statement doesn't have a Q and it has a tilde Q, right? You guys see that? But there is a Q present in some fashion, so there will be a column for Q. So there's always going to be a column for the two individual statements given as is without any tildes. Then anything else that's happening to those statements becomes part of the system of what we're working with. There is a tilde Q, so I need a column for tilde Q. Okay, if there had been a tilde P, I'd put that in there too, but I don't need it because there's not one. So we also don't want to just add things that aren't necessary in. And then the last thing that I will do is all of it together because I've got the individual pieces all present there. The P, the tilde Q, they're present. So the final column is in this case, it's an and statement or a conjunction of P and tilde Q. Now, even if you can't go any further, you should be able to line up the heads, like we just did that, all the headers for the rows, and you should be able to complete the first two columns, always. The first two columns always, even without the headers, you should be able to do. What's the first column going to be for the P column?
True, false, false.
Yep, true, true, false, false. And what about the column for Q?
True,
True, false, true, false. Okay, so that will always be the same, doesn't matter what comes next. However, what comes next now is a tilde column, right? It's a negation. We did those last time as well. Negation means it's going to be exactly the opposite of whatever it was before. So in this case, it says the negation of Q, so it needs to be the exact opposite of the Q column. So it will say what? False, true, false, true. Okay, is that all right? All right, and then I'm going to actually take a look at the P column and the tilde Q column. So in some sense, I'm sort of ignoring the Q column in the middle. Okay, I only want to look at the first one and the last one because those are the ones that are referenced in my column header that I'm working on now. And I want to make an and statement. And when is an and statement true? What does it take? They got to both be true. Okay, so they got to both be true. So if I look at sort of row 1 here, I've got true in my first spot and I have false in the second spot. What does that create? That is a false statement. Row 2, I have true in the first spot and I have true in the last spot. That's a true statement. And the last two are automatically false. How can you know? Real quick. Yeah, they both start out false, right? I don't even have to go to the second column to check. I'm doing an and statement. They start out false. It's going to be false. Okay, so, and once again, it's an and statement. The majority false is at the end. That side, that tracks. It works. And so that gives us sort of some confidence that we've done correct things. It doesn't verify it, but at least makes sense. Okay? All good? So this is how truth tables work. We're going to get to some more of like what we're going to do with them later, but some logically equivalent statements. So logically equivalent statements are two statements that have the same truth value in every possible situation. If those statements are PQ, logically equivalent means putting 3 lines between them. Okay, that's how it's written. It means they're identical. And an example of these logically equivalent statements are De Morgan's laws. Now, my statement on here of the De Morgan's laws don't have 3 lines between them because there's not actually a tool, an equation editor inside of PowerPoint and Word and so forth that has 3 lines. At least if there is, I don't know where I can find it. So there should be 3 lines. This should actually have a 3rd line on it. Let's see if I can get one there that actually looks thin enough that it makes sense. I'm going to zoom in for just a second and see if I can make it. It's not too bad. Let's go with it. It still shouldn't look as thick as it does, but that's all right. So De Morgan's laws actually tell us what happens when we negate statements, which start out as conjunctions or disjunctions, okay? So this first one of De Morgan's laws is an and statement, okay? It's a conjunction. And what we see happen is a negation outside of a set of parentheses. So the way that that works is that negation sort of moves its way through kind of like a negative would in algebra, but it affects three things. It affects P, so it becomes tilde P. There's a typo. It should affect Q, so this should say tilde Q. I'll fix my screen in just a second. And it changes the and into an or. Okay, so this right here should say tilde Q. Sorry about that. Okay, so it affects all three pieces. And notice the same thing happens when we do a disjunction. So when I have the negation in front of a disjunction, which is an or statement, it affects the P, becomes tilde P. It affects the Q, it becomes tilde Q. And it affects the or in the middle, and the or changes into an and. Okay, these are logically equivalent statements, and De Morgan is the one who is credited, I guess, with at least the formalization of this idea, okay? So what we're going to do actually next is verify what it looks like when you have logically equivalent statements in a truth table. Now, it told us in the definition what it's supposed to look like. It says there are two statements that have the same truth value in every possible situation, okay? So let me show you what that means, because it's actually referencing a truth table in that description. So let's skip 3 for a second. We'll do 4 so I can show you the logically equivalent. I think I need to shift some of these in terms of my order of things. So let's do example 4 together first. So it wants us to verify that both, I got to do 3 to do 4. That's probably why it's in there. I was so excited about doing 4. I guess we got to back up and do 3. We're going to use De Morgan's laws first to write it out, and then we'll prove that it actually worked. All right then. So I have a tilde. I'm supposed to be finding the negation of P and tilde Q. All right, so all three pieces that are on the inside have to be negated. So what happens when I negate the first piece? What do I get? Tilde P. What happens when I negate the upside down V? Turns upside down, right? So I had a V, now an upside down V, now it's actually a V. And what is the negation of tilde Q? Q. That would be Q, very good. Okay, so what we're going to do is we're going to create a truth table where we actually show that these two things really are logically the same thing.
Is it 3 lines or is it 2?
It doesn't matter that much. So it's asking us to write it. So technically, yes, if you leave it off, it's not a big deal. But yeah. Okay, so we're going to create a truth table. The truth table has a column for P and a column for Q, just like they have been having all the way along. And we're going to work with the left-hand side first, okay? So the left-hand side has P, it has Q, and it has tilde P. So we're going to do a tilde P column. I didn't mean P, I meant Q. A tilde Q column. There we go. Okay, the left-hand side. So just like with algebra, we're working inside the parentheses, and then we move outside the parentheses, okay? So I haven't quite finished the inside of the parentheses. I need to do the inside of the parentheses sort of all together now, all the pieces merged together. So I need a column that represents everything that's inside those parentheses, which would be P and tilde Q. Okay, this is actually the truth table we did before. I was thinking it was, okay? So the truth table we did before already did this, so we should be able to move through this piece of it pretty quickly. So when we did this one before, we said that we had true, false, false, and then true, false, false. They alternated false, true, true. And then we had our final statement, and our final statement was false, true, false, false. Okay, so all of this was done on example number 2. Okay, is that all right for everybody? Just kind of copying it over. The next column's new though. The next column actually takes the negation of this. So I need the negation of the P and tilde Q column. That and shouldn't really look like an A. There we go. So I'm going to take the column that I have, right? And I'm going to do the negation of that column. All right, that's fine. My touch sensitivity is really high today. I don't know why. All right. So if I take the column that I've created at the very end here, false, true, false, false, and I do the negation of it, what will it be? Okay, true, false, true, true. Is everybody good with that? Okay. So in some sense, this is the end of the truth table that represents the left-hand side. Okay, and I will actually change the... All right, that's not working at all. I wanted to change the color. We'll just do it in red like that. Oh, now it's getting erased for me. Of course it is. Okay, the other side, the one that's underlined in red, is what we're going to do next. Now, looking at the columns that we have, we want to make sure that all the columns that are represented by the part that's underlined in red are present, and one of them's not. What do I need a column of that I'm currently missing? I need the negation of P. There is no negation of P column in my column headers so far, and that is actually right here, so I need it. So I need a negation of P column. So we're gonna have to go all the way back to the very front line, right? What will the negation of P be in terms of T's and F's?
False, false, true, true.
Good, false, false, true, true. And then what we're going to do is that we're going to make another column header. The column header that we need is our last column. We already have the negation of P, we just did it. We already have Q, it was already present. So we're ready to put it all together at the end. This is the P tilde P. Wow, not at all what I meant to do. Let's try again. Tilde P, and then it's an or statement Q. So now I'm looking at the Q column here, and I'm looking at the tilde P column right here, okay? I'm marking mine in red to try to draw our attention to it and try to block out some of the other things that are going on because they're kind of far apart. So this is an or statement. When is an or statement true?
When one or both.
When one or both of them are true. So all I need in the parts that I've sort of circled in red is at least one true statement between the columns on a particular row for the row to be true. So the first column, I actually have true, and then the next one false for row 1. So what will that be in a truth statement? That is true for a disjunction. On the second row, I have false underneath Q, and I have false underneath tilde P. That is false. Third row, I have true underneath Q, and I have true underneath tilde P. That's true. And then the last one, I have false underneath Q, and I have true underneath tilde P. That's true. And what we want to show is what we've just shown. So let me verify for you that we did what we were asked. We were asked to show that this one right here, the tilde P and Q, which was the left-hand side over here, right there, to P and tilde Q, this one right here, is going to be equivalent to this. And check it out. This is the column that was the original one. That's not what I meant. This is the column that was the original left-hand side. So this is my left. And this is the side that's on the right. And what do you notice about the columns? They're the same. They're exactly the same. And that's what it said over here needed to happen. They need to be the same truth value in every possible situation. Okay? Another way of saying that is that the columns that represent them have the same true-false arrangement, exactly the same order and so forth, as you look down them in the truth table. Okay, that's verifying that that actually worked. Okay, let's take a look then at De Morgan's laws a little bit more. So De Morgan's laws talk about how we negate things, right? And when we looked at De Morgan's laws, it said that we sort of like move this negation through things in 3 places. So there's 2 statements, right? 2 individual statements. And then there's something in between them called a connective. Okay, something that connects them, the and or the or. So when we're moving it through, we have to negate all 3 pieces, right? When we make a negation of a statement. So the first thing we're doing when we're looking at De Morgan's laws for an actual statement is what the individual statements are. So one statement here is, it is not sunny. And the other statement is, I will go for a walk. Does that make sense? The connective in the middle is the word and. And I do like to draw it like this because then I can see 3 distinct pieces and make sure that I negate all 3 of them. The most common error students make is forgetting to change the connective. They do the other pieces too, usually just fine. They just forget the and turns into an or, okay? So if I circle it, perhaps it will draw my attention to the fact that that's something that needs to be changed as well. So what is the opposite, the negation of it is not sunny? It is sunny, just like it is outside right now, right? So that's the negation. It is sunny. Or, yes, the and becomes an or, right? This is important that that switches in the middle. And then I will go for a walk. What's the negation of that? I will not go for a walk. Now, let's actually talk about logically, like in terms of our English, our vocabulary, our context clues, why this actually makes sense. So let's say you make this statement, it is not sunny, and I will go for a walk. That was yesterday morning. It was raining outside, right? Do y'all remember that? It was cloudy and rainy, okay? So if that were a statement that were happening, it means, and it's true, right? It means both of those things would be true at the same time. It wasn't sunny, and I did walk, which actually is exactly what I did yesterday morning, oddly enough, okay? But in order to negate that statement, what has to be true is that either one of the original statements just needs to be wrong. They don't both need to be wrong, just one of them does, okay? So I can either take the first piece and I can make it false. That's what a negation does. Or I can take the second piece and I can make it false. But I put the word or between is because I don't really need both of them to be false to actually like make my statement false. I just need one of them to mess up. Right? This is our guests that were coming in. All we need for the and statement to be false is them to not teach math or them not to be a mom. I don't need both. Y'all with me? That's what's happening with De Morgan's laws. They're talking about what's the smallest thing I can change. That's what a negation is. What's the smallest thing I can change and still make the statement not a true statement anymore? Okay? So this is what De Morgan's laws does in this example of that happening. All right, so the last thing we're going to be looking at then is called conditionals. They're also called implications if you'd like to write that down. A conditional is a statement that's expressed in the form if P, then Q. You can also read it P implies Q. And the notation for that is an arrow. And you can kind of see from that notation why P implies Q works nicely. You know, you sort of like read the arrow as the word implies and go from left to right, that sort of thing. The hypothesis is the if part. You know, if this happens, then. If. That's my hypothesis. And then the conclusion is the then part. It's what follows. So the first thing we're going to do with these implication kind of statements is that we're going to flip back and forth between what they look like in symbols and what they look like in sentences. Okay, the structure, the language component of them. I need to build you the truth table first. I apologize. It's not actually written in my notes, but it's definitely in a space for it in my notes. So let's do the truth table first. All right, so we're going to draw a 2-column truth table, right? 3 columns really, I guess. And we've got a column for P and a column for Q, and then we've got the P implies Q column. And my statements about math and moms don't really make a lot of sense here. So we're going to change my P's and my Q's so that they have a structural context that might be a little bit easier to understand what's going on. This one's the most confusing in terms of the truth table, okay? So we're going to let P be the statement. We'll not use I, we're going to use she. She leaves her shoes in the living room. Okay? That's my column P, or my statement P. Q is going to be the statement, they get taken away. We have issues with shoes at my house. This is actually one of our house rules. We're gonna see how it works. Okay. So we know how to fill in a truth table for the first two columns, so we're going to fill those in. True, true, false, false, true, false, true, false. Okay, so let's say that the first statement is true, okay? In fact, I should tell you first that the P implies Q, like this is the house rule. So that's the rule we're following when we're looking at this. I mentioned that, but let me make that a little bit stronger case. So the first statement is, she does leave her shoes in the living room. They do get taken away. As with every other statement that has two trues in the row, this is a true implication statement, okay? It happens. But if I'm really following the rule, the next one can't happen. Because the next one's actually saying she did leave her shoes in the living room, but they didn't get taken away, right? That's what the false would mean, is that we didn't follow through on the rule, right? It's not a very good rule if you don't follow through on it, right? It's a false statement if you did that, right? That would make my rule a false rule if I don't follow through on it, as said. Now, the next two are the parts that trick people up. So those two people are usually good with. It's the next two lines. So the next two lines actually talk about the fact that she doesn't leave her shoes in the living room, right? That's what the false would mean underneath that column. And one of them results in the shoes being taken and the one results in them not being taken. Okay, are you with me? Those both can be true statements. And let me just give you a very picturesque image. Maybe she didn't leave him in the living room and she left him in the kitchen. What do you think is going to happen? Well, if I'm following through with my rule, the point wasn't really the living room, was it? The point was that they weren't where they were supposed to be, and the kitchen is also not where they're supposed to be. So them getting taken, this false implies true statement, could still be a true statement, okay? But what if she took them and put them back where they were supposed to be? They're back in her bedroom closet, ideally, right? Then the next statement, the fact that she didn't leave them in the living room and they didn't get taken away, is also a true possibility that could happen. So the default on both of these at the very end is that they could create, because we don't know much more about the situation, true statements. So when you're looking at a truth table for an implication, you see a lot of true statements here at the end, right? Just like our or statements were, a lot of true statements. And the only one that is not true is the one right here in the middle. That's true implies false. Because if true implies false happens, it means that the rule, the statement, was not followed, right? The if-then statement that you created was not followed. In any other situation, it either was followed on the top, or we have no way of knowing for sure on the bottom if it was followed or not, so therefore it could be true. Okay. So let's go and look at some terminology, switching things back and forth now. So this first one says, P is the statement you build it, and Q is the statement they will come. Do y'all know what this is from? It's a really old movie. It's a movie from my childhood. And I think it was before my childhood. It was old then, yeah. It is called Field of Dreams. It has Kevin Costner, and it's a baseball movie. It's a very well done movie, by the way. So if you're into older style movies, you should watch it. So this is where this is coming from. And we're going to take these statements and we're going to rewrite them. Notice on the very first one, though, the if is not at the beginning. Do y'all see that? It's in the middle. Well, if the if is in the middle, we still start with the if when we're rewriting it. So this if and what follows is still the beginning of my statement. If you build it, that's the first piece, even though it's occurring in the middle, and we put it at the beginning. And it says, they will come. So the they will come then is the Q, right? So this is P implies Q. In a funny order, agreed, but we talk like this all the time, right? We often move our ifs to the middle of sentences. We're usually trying to emphasize the result of what's going to happen, and that's why we say it first. Okay, but we do this all the time. Now the next one, the if's at the beginning, so we just start at the beginning. It says, if you do not build it. So what is if you do not build it going to be in terms of our symbols? Not P, which is the tilde. Tilde P. And then I have the then statement, right? Then comes next, so I've got my arrow. It says they will not come. That is tilde Q. Okay, so tilde P implies tilde Q on this one. Okay, so our next set is going to do the opposite. We're going to actually start with symbols, and we're going to write what happens in words instead. So we've got a different statement. So P is the statement I have sinned, and Q is the statement I need forgiveness. okay? So this actually incorporates an and statement at the beginning, right? We've got that upside down V as the first one. So it's P, upside down V, and then Q. So P was the statement what? I have sinned. What does that upside down V mean again? And. So we put the word and. And then Q comes next, and what's Q? I need forgiveness. And that's all of us, right? That's all of us. Now the next one actually has an arrow. Okay, so this is the if-then one. So even though there's an arrow, we still start with the word if in front of it. Okay, so that's how it begins, if. Now it says tilde P, and P was the statement, I have sinned. So what is tilde P? If I have not sinned. What comes next? Then. Then what?
Ours has a tilde, but yours doesn't.
Okay, a typo here. So yours has a tilde Q here?
Yeah.
Okay, cool. Thank you. We'll fix it so that it matches yours. Okay, so if I have not sinned, then, and what's tilde Q? Yeah, I do not need forgiveness. And that applies to one and only one person, right? That's Jesus right there. Okay, he's the only one who didn't need forgiveness. All the rest of us do. Okay, so we're just changing them to symbols, changing the symbols into words, and back and forth. All right, our last piece in this of information in this section are adjustments that we make to implications when we change their order around. So implications are conditionals. Our original statement is an if-then statement, okay? So it goes if, then, right? This is what it does. And we write it as P implies Q like this. Okay, so that's just the statements we've been working with already. If you want to find the converse of an implication, what you do is you flip the P and the Q around. So P moves to the end and Q moves to the front. So it's Q implies P, like that. Now, that's not the same statement. I'm not telling these things are equal. That's not what I'm saying. But this is called the converse of the original statement. Now, the inverse of the original statement actually keeps things in the same order, but it negates them. So the order is P and then Q, but in front of each of them is a tilde. So I have tilde P implies tilde Q. And then the last one does both. So I switch the order and I put negations in. So this one is negation of Q implies the negation of P. And you will explore which of these things are equal by some actual statements in your homework, okay? You probably have a feel for this after I show you one more thing here. But this is what this looks like for the statement, the converse, the inverse, the contrapositive. So I want to push pause for a second. Actually, I think I can keep, YouTube might not let me. So I'm going to push pause on my video, and then I'll, I hadn't thought about how this works. I can't pause it in the same way. Okay, let me do the next slide, but then I want to show you a YouTube video, but my concern is that if I put the YouTube video inside of my own YouTube video, it's probably going to flag something as copyrighted, and then it's going to fuss at me. So we'll just do this here. We'll go in the reverse order, and we'll see how it goes. So here's an example. We're going to create the converse, inverse, and contrapositive for the statement, if I'm a monkey, I have a tail. Notice the word then is not there, but it's implied, right? And we do this with our language all the time as well. There is an implied or an understood word then that's right here. If it helps you to write it there, do so. All right, so converse is what we'll do first. The converse takes the two statements. Our statements are, I'm a monkey and I have a tail, and it switches the order. So what will come first in the converse? Yep, so it still starts with an if, thank you very much, and it's if I have a tail. Then we've got the word then. What would follow that? Then I am a monkey. So that's my converse. Now the inverse, again, we're going back to the original statement, but the original statement. The order stays the same, so monkeys at the beginning, tails at the end. But instead, I negate both of those individual statements. So what is the logical opposite of the statement, if I am a monkey? Like, the if is already there. Sorry. What is the logical opposite of the statement, I am a monkey? I am not a monkey. Then, and now I need the logical opposite of the statement, I have a tail. I do not have a tail, or I don't have a tail. And then the contrapositive flips both. For the contrapositive, we're flipping the order and we're negating, okay? So looking back at the original statement, I start with what's at the end. Well, I start with if, and then I start with what's at the end. I need the logical opposite of the statement, I have a tail. If I do not have a tail, then, and now I'm going to go back to the beginning. Yes, then I am not a monkey. These four statements are not equivalent to one another. They don't mean the same thing. However, they do occur in pairs. Two of them mean the same thing, and two of the others mean the same thing as well.